Hello, statisticians. Mr. Youngsaver here from Skew the Script. A fun topic today. How insecure are men statistically? We're going to analyze this by looking at the addition rule in probability. Let's skew it. Today's lesson is on the addition rule. This is lesson 5.2 in our course sequence. So say a 36-year-old heterosexual man wonders to himself, how can I make my online dating profile a little bit more appealing? He turns to the paragon of our culture, romantic comedies, and he notices a few trends that our insidious social standards tend to favor tall, wealthy, heterosexual white dudes. This is what we see in these romantic comedies almost to the T. And he's thinking to himself, okay, to be more appealing, I should make myself seem my online profile a little bit taller and a little bit wealthier. My question is, how often does this happen? What percent of heterosexual men are insecure enough to actually lie on their online dating profiles? And can we discover that through the tools of statistics, data science, and probability? That is our task for today. If you want to follow along using guided notes, you can print them up at the URL on our website here. Before we get into the topic at hand, let's talk about some probability notation and rules around unions and intersections. So say we have a Venn diagram of two events, A and B. PA means the probability that event A occurs. PB means the probability that event B occurs. PAC is the probability of event A's complement, meaning the probability that event A does not occur. So everything except for event A. This is a new symbol here. The upside down U is AND. That's the probability that event A and B occur. And there's a very specific definition for AND in probability. AND means both. AND means they both occur. And this is called the intersection of events A and B. You'll notice on the Venn diagram, it is where the two intersect, where they both occur. Or also has a specific definition, and it's symbolized by that right side up U. P, A, or B, probably event A or event B occurring means that either A happened, or B happened, or both. So it could be one or the other or both. It's inclusive of all those possibilities. This is the union of events A and B. So and is only when they both occur, or as one, the other, or both, inclusive of all those. Lastly, if you look at the complement of A or B, this is the probability that neither A nor B occur. It's not A or B. So it's everything outside of these Venn diagram circles. So that's some of the notation we're going to be using today and going forward in our probability section. Now, let's talk about the addition rule and probability models. And let's talk about the data we're going to use here to explore our topic today. So I found some data on public online dating profiles from 2012 on the site OkCupid. Full data source is listed below. Now, people identified as, sorry, the data set is of people who identify as age 36, male, heterosexual, and living in the San Francisco area. And I collected the data for each profile that reported their height and their yearly earnings. Now, why am I looking at age 36 profiles? Well, it's a lower bound for the age when men typically earn their median salaries. And it's also an age when men who are dating online might really start to feel the pressure to find someone and settle down. So we estimated the 2012 median yearly earnings for individual men in San Francisco County to be $59,397 at the time. That's kind of an upper bound estimate. And the male median height in the United States is estimated to be around 69.2 inches, or about 5'9". Remember what the median is. The median is the 50th percentile of the data set. So in America, or sorry, in the United States, we'd see 50% of people would be above that height, 50% of people below that height. And in San Francisco County in 2012, 50% of men would earn more than that amount or less than that amount. So on OkCupid, not in the general population, but on OkCupid specifically, what is the probability of finding someone who is taller or wealthier than the median? So I took the data and I categorized it in this way. For the profiles that reported that they earned less than median income, I recorded them as a low earner. For those who reported that they earned more, it was a high earner. For those who said they were shorter than the median height, I said short. For those who reported they were taller than the median height, I reported them as tall. Now, in the OkCupid data, both those categorizations, we found 21 people reported as short low earners, 22 reported as tall low earners, 48 as short high earners, and 101 as tall high earners. So if we were to just do our dating completely randomly and we randomly sampled a mate from this data set, we would see the following probability model with the following probabilities for each of those categories. Now let's do a validity check really quick. Is this a valid probability model? Well, we need to first check, are all the probabilities 0 and 1? They are. Do all the probabilities add up to 1? Yes, we have covered the entire sample space. So let's let T equal the event of selecting a tall man randomly from this pool, and H the event of selecting a high income earner. So first, let's find the probability of selecting a tall man. Well, there were 2 of these categories that had tall men in it. So we're just gonna add those together. We have a 64.1% chance of selecting a tall person from the OkCupid dataset. So this is a much higher probability than the population of the US as a whole, because remember, 50% should be above the median. So we're already saying OkCupid people tend to be tall. Well, at least they report being tall. Now, let's look at the probability of selecting someone who's tall and a high income earner. Remember, and means both. So we need to find someone who is both tall and a high income earner. That's one category there, 52.6% chance of that. Let's find the probability of finding someone who's tall or a high income earner. Remember, or means one, the other, or both. So there's 3 categories that fit there. They're either tall, a high earner, or both. And we add those up to get 89.1%, a really high chance of finding someone who is tall, a high earner, or both, at least according to what they report online. Again, raised eyebrows. So usually when we talk about OR conditions, they involve a lot of addition because it's inclusive of a lot of categories. And we're going to come up with a simple addition rule, and we're going to complicate it a little bit later, but generally OR means add. Whenever you hear or a union, that means you're adding things together, you're bringing together a bunch of categories. So OR means add. We're going to work with that rule going forward. Let's talk about that simple addition rule in two-way tables. So here's a two-way table of the same data. And let's find the probability of finding someone who's tall and not a high income earner. So and means both. So that's these people here are both tall and not high income earner, low income earner. And we see the 11.5% of the people on the site are that. That's our chance of getting someone like that. Probably selecting someone who is a high income earner at random. Well, we can add up the 2 high income earner categories. Divided by the total of 192, we get the percentage. We can also just get the column total because the two-way table calculates that for us. We get 77.6%. Again, raised eyebrows. This is a much higher probability than we expect in the population of men in San Francisco, given that we're using the median, the 50th percentile. So now let's find the probability of finding someone who's tall or a high income earner. Remember, or means one, the other, or both. So that includes all these categories of people who are tall, a high income earner, or both. And remember, or means add. So we're going to be adding these together to get the full probability, 89.1%. Now, you might be thinking, well, this seems like a lot of work. Maybe instead we can use a shortcut. Instead, let's add the column total for high income earner and the row total for all the tall people, because the totals are already given to us, so just add them together. That's very reasonable. So we add those together, and we get a numerator 272, and it's a 142% chance of getting someone who's taller. Wait, what? 142%? That's above 100%. That's not a valid probability. What happened was when we used those 2 totals, we double counted the people who were tall and a high income earner because they appear both in the column total for the high income earners and the row total for the tall. So what we need to do is subtract that off once to account for that double counting. When we do that, we get the same probability we did before when we were a little bit more careful about picking our categories. So this introduces us to the formal or the general addition rule that yes, or means add. The probability of A or B is probability of A plus probability of B, but we have to subtract off probability of A and B. We subtract off for double counting. So instead of using this formal addition rule, I would encourage you to use what I call the intuitive addition rule. So don't worry about formulas when talking about probability. They can often confuse. Instead, use this intuitive rule. When you see an or condition, or means add, and also avoid double counting. My advice is to use this general guidance when going through probability problems that can often be complex. So also one side note, you might be given two-way tables that are not counts, but probabilities. So what they do is they take the grand total, they divide each category by the grand total, and they come up with the percentages or decimal probabilities already for you. And these work in the same way, it's just they've already done the dividing for you. So for example, if we want to find the probability of tall or a high income earner, we add those together, divide by the double counted portion, and we note that it's already kind of divided for us in the probability table. We did the same division in the first table, we're dividing each one by 192, and we get the same exact decimal. So it's the same exact thing, so they kind of do a step for you. So just look out for that. Now, let's start with the addition rule in Venn diagrams. So we can put our categories into a Venn diagram. The people who are high income earners and tall are the intersection between those tall and high income earner circles. That's 101. 48 were high income earners, but not tall. 22 were tall, but not high income earners. And then 21 were neither tall nor high income earners. So we put those there. Find the probability of one circle, the probability of getting a high income earner. We add up the whole circle total, divide by 192, and we get that probability. Find the probability of both the and condition. We get the intersection. So the probability of finding someone who's both a high income earner and tall is 52.6%. Find the probability of someone who is a high income earner and not tall. We just get the high income earner without including any of the tall circles. So that's 48 out of 192, or about 25%. Find the probability of someone who is not a high income earner. We add everything outside the high income earner circle. So that's 22 plus 21. Out of 192 is 22.4%. We'll also use the complement rule, 1 minus the probability of high income earning. So that's 1 minus what we got before, which again, it gives us 22.4%. And then we can also find the probability of tall or high income. So again, we need to make sure we don't double count. So let's do this carefully. Or means one, the other, or both. So let's add up those three categories that fit in tall, high income, or both. 22 plus 101 plus 48. We're going to add because or means add, and we're going to avoid double counting. Add those up, we get a numerator of 171. If you want to use the full circles, we can, but we need to adjust for double counting. So we add tall plus high income. That's the 123 in the tall circle, plus the 149 combined in the high income circle. Then subtract off the 101 who were double counted for being in both, and you still get 171. So either way works. Make sure you don't double count. When we divide that by 192, you get 89.1%. So just like with two-way tables, Venn diagrams can also be presented in a probability format. They just divide by the total denominator, and you get the percentages there. Now, let's talk about mutually exclusive events, a specific type of set of events. Mutually exclusive events are when they have no intersection. They cannot both occur. They cannot co-occur at the same time. So their Venn diagrams look like this. There is no intersection between them. It's not possible to have A and B together. So for mutually exclusive events only, we don't have to worry about double counting because there's no intersection. So for mutually exclusive events, probability of A or B is always simply the probability of A plus the probability of B. We don't have to worry about double counting. So that's nice about mutually exclusive events. So let's discuss our initial topic today. If we randomly sample among the OkCupid profiles of age 36 heterosexual men, the probability of selecting someone who is above median height, we found this earlier, was 64.1%. Probability of selecting someone who's above median income for the area of San Francisco for men was 77.6%. So these probabilities should only be 50% in the population, but on OkCupid, apparently, these are more eligible bachelors. They have high heights and high incomes. So the question is, are single heterosexual men on OkCupid that much taller and wealthier than the rest of San Francisco? Well, if you look at the data for the median income / earnings of men over the course of their lifetimes, we see a gradual rise peaking at about age 55. This is national data. If you look at the OkCupid data and look at the ages of the people on the data set, we see a dramatic rise from age 22 to age 32, and then it's pretty steady after age 32. To show you how dramatic this rise is, let me put those together. The percent change from the age 22 income, median income, is huge for OkCupid and not so much in the general population. And remember, this is percent growth, so it's taking into account that initial amount. So taking into account that and taking into account these, do you believe that many of the men on OkCupid are insecure enough to be lying on their profiles? Provide a statistical explanation for your answer. That's it for today's statisticians. Have a good one.